Section 9.2, this is on multi-stage experiments. So in 9.1, we looked at simple events or one-stage experiments. Now we're going to look at multi-stage experiments, where we do something and then we do something else and then we do something else. So, kind of like the, name depicts, right? The name suggests is multi-stage experiments. We're going to use something called a tree diagram to give us a visual of a multi-stage experiment. There are other ways of doing this. One of them is called an area model, and it's pretty darn cool. I'm actually going to put a link on my website for you to watch that video because it's a pretty cool way of doing it with the area model. The tree diagrams are pretty common to see. They're probably the most common. But they're going to give us a visual of these multi-stage experiments. Okay? Now, the trees are helpful because there is this nifty little multiplication rule that says that for all multi-stage experiments, the probability of an outcome is the product of all the probabilities along the path to that outcome. So that's what makes the trees pretty useful. So let's draw a tree diagram for flipping a fair coin twice. So we're going to start over here, and we have one outcome, and then we have another outcome. Okay, so we flip and we get heads or we get tails. Now for my second flip, which, Lord have mercy, I swear, I do not give myself enough room. I try to keep my notes, to where they don't take up a trillion pages, but that means that I end up cramping everything in. All right, so let's do this. Heads, tails. Now, if you flip heads the first time, you got to flip it again. Well, your options now are still heads or tails. Here, heads or tails. Now, each one of these probabilities, these are theoretical probabilities, each one of these probabilities is 1/2. So we typically write the probability along that branch. So now if we were talking about finding the probability of flipping a fair coin twice and getting heads, heads, what would that be? Well, it followed the branches, right? Heads to heads. Multiply those, we would get 1/2 times 1/2, we would get 1/4. That makes sense because we have 4 total outcomes. You can have 2 heads, heads and then tails, tails and then heads, or tails and then tails. So there's 4 equally likely outcomes. Yeah. Now, let's suppose that you have a jar that contains 2 red marbles and 1 blue marble. Draw a marble, record the color, replace it, and then draw it again. This whole thing of replacing or non-replacing is going to be a big deal. The sample space for this would be red, 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 blue, blue, red, blue, blue. Right? There's only 2 outcomes, red or blue. However, there's different numbers of them. So the red are slightly more likely. So even though we have 4 outcomes, just like we did with the heads or tails, these are not equally likely outcomes. Because the red, there's more reds than there are blue. So here's my tree diagram. And I put the probabilities on here. So where did I get a probability of 2/3? Well, it's because there's 2 red marbles out of a total of 3 marbles. There's 1 blue marble out of a total of 3 blue marbles. Because I drew a marble, wrote down the color, put it back, and then drew again. This is my second color draw. All right, second marble draw where I'm recording the color. Because I put the marble back, my probability is still 2/3 for the red because I put that red one back. My probability is still 1/3. So you can see my outcome is following these branches, red, 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 blue, following this branch, blue, red, or blue, blue. So there's my outcomes. The probability to go along with those outcomes comes from multiplying the probabilities along the branches that lead to red, red. 2/3 times 2/3 is 4/9. 2/3 times 1/3, 2/9. 1/3 times 2/3, 1/3 times 1/3. Now notice that these probabilities, this makes up the entire sample space. These probabilities better add up to 1 or else you've missed something. Okay? So in this particular example, the first marble drawn is the first event, the second marble draw is the second event. So that's the multi-stage experiment. Right? So I've got two separate things happening here. Now, the first event's outcome had no event on the second. Sorry, had no effect on the second because we put the marble back. But how would this change if we drew the marble and we did not replace it? So let's say that we did not replace the first marble. What does that change? Well, it changes a lot. So how do the probabilities change? So I didn't list the probabilities on this one. I redrew the tree and the outcomes, but we're going to do the probabilities together. All right, so there's still 3 marbles, 2 of which are red. So we still have a 2/3 probability for red and a 1/3 of blue. This is still the same scenario as that previous one. 2 red, 1 blue. But here's the thing. This tells me I drew a red and not put it back. So I have 1 less red. So what is the probability now of getting a red? If I have already pulled out 1 red, I've only got 2 marbles left, and only 1 of them is a red, and 1 of them is blue. Okay. So I've got, wait, was it 2? It was 2 red and 1 blue. I'm finding the red pen. There we go. 2 red, 1 blue. There we go. Now, this says you pull out a red. Okay, so boop, there's a red. Now, I've got 2 total. 1's red, 1's blue. So what's the probability of getting a red now that this guy's gone? Well, it's 1 out of 2. This branch says that you pick out a blue first. So there's the 2 red, 1 blue. Now, let's suppose I pick out a marble and it's blue. Now, what's the probability that my next marble, with that blue one being gone, I'm not replacing it, now what's the probability that I'm going to get a red? There's 2 marbles, both of them are red, so that's 2 out of 2. What's the probability that I'm going to reach in this bag and pick out a blue marble again? That's not going to happen. There's only 1 blue. I've already picked it out and I didn't put it back. So this changes because of this whole not replacing business. All right, these probabilities are going to come from multiplying those outcomes. So this is going to be, give myself enough room here, 2/3 times 1/2. It's going to be 2/6 or 1/3. That's going to be 2/3 times 1/2, which is 1/3. How did I know that? Because I just did it. This one's going to be 1/3 times 2/2, which is 1/3. You know how I know that? Because that's 1. 1/3 times 1 is 1. Or sorry, 1/3 times 1 is 1/3. And this one's going to be 0 because it's 1/3 times 0/2. Notice these add up to be 1. 1/3 plus 1/3 plus 1/3 plus 0 is 1. Since we're not replacing the first marble, the first draw affects the second. So we say that these 2 events are dependent events. Okay? So if you replace the marble, these are independent events. Whatever you pick for the first one, no bearing on the second one. Has no effect on it whatsoever. If you don't replace the first marble, now we've got a dependent event. These probabilities are dependent on whatever you picked first. They do have some kind of an effect. Now, when working with probabilities, remember, and means multiply, or means add. That's a really good rule of thumb when you're talking about probabilities. That and means multiply, or means add. All right, a couple plan to have 3 children. Let's draw a tree diagram to show all the possible outcomes, and then we're going to use the tree to find the probability of having boy, girl, girl in that order, 2 girls and 1 boy in any order, 3 boys, or at least 1 girl. So let's start off with a tree diagram, and then we'll be able to answer all these questions from the tree diagram. This is going to be very similar to the first one I drew with the coins, the heads or tails, right? Because it's just boy, girl, 2 outcomes. So let's see if I can do this without it being a hot mess. Doubtful. All right, so let's say boy, girl, boy, girl, boy, girl. Okay, first child, second child, third child, boy, girl, boy, girl, boy, girl. Already a hot mess. Boy, girl. You guys expect nothing less from me at this point. How many outcomes do we have? We have a total of 8 outcomes. That's because there's 2 outcomes, boy or girl, and 3 children. So you have 2 outcomes for the first child, 2 outcomes for the second, and 2 outcomes for the third. 2 times 2 times 2 is 8. So let's list out those outcomes. Now we're just going to follow these branches, okay? So let's start with the first one's a boy, second one's a boy, third one's a boy. So we have boy, boy, boy in that order. Then this is the end of boy, boy, girl. So that finishes up this little sprig. Now let's go from this girl. So boy, girl, boy, and boy, girl, girl. I'm trying to write it right where, that little tree branch ends. Here's the 4 outcomes where the first one's a boy. So let's look at the pattern here. Do you see my pattern? Boy, 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 boy. Boy, boy, girl, girl. Boy, girl, boy, girl. All right, now let's follow the girl trail here. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. The only reason I'm leaving these spaces is I'm trying to coordinate my outcome with the end of the branch there. So here are the 8 possible outcomes for having 3 children. Let's talk about the probabilities. Well, the probability, we're going to go theoretical here and say that it's a 1/2 probability every single time. Even though I don't think it typically is. I think experimentally, isn't it like slightly more likely that you're going to have a girl? I mean, not much. Like 0.51 versus like 0.49, 51%, 49% kind of thing. So theoretical probabilities on here. So what does this make this outcome? What is this probability then? 1/2 times 1/2 times 1/2 is 1 out of 8. Turns out these are all equally likely outcomes. I know it doesn't feel that way, right? Because you think, okay, if you have 3 children and they're all going to be girls or they're all going to be boys, you think, well, that's pretty unlikely. Well, if you talk about the order, right? If you're just like, oh, well, the probability of having at least one boy, you know, that's one thing. But if you're talking about the probability of a specific order of like girl, boy, boy, or girl, 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 they're all as equally likely. Now, let's use this tree to answer these questions. So what is the probability? So for part A, of boy, girl, girl in that order. Boy, girl, girl in that order. That's 1/8. B, 2 girls and 1 boy in any order. All right, 2 girls and 1 boy. 2 girls, 1 boy. 2 girls, 1 boy. 2 girls, 1 boy. 3 possible. So there's 3 of those outcomes. You can do this by saying there's 3 out of 8 outcomes, or you can do it because they're all equally likely. You can just add up the 1/8 plus 1/8 plus 1/8. Part C, the probability of having 3 boys. 1 out of 8. There's only one way that's going to happen, right there. Oh, and then we have D. At least 1 girl. At least 1 girl. That means 1 or more. At least 1 means 1 or more girls. Okay, so there's 1 girl, 1 girl, 1 or more. 1 or more, 1 or more, 1 or more. 7 out of these 8 have at least 1 girl. So if having 3 kids, it's pretty likely that you're going to have at least 1 girl. Example 4, we're back to decks of cards. You draw 2 cards from a standard 52 card deck without replacement. That's big. Pay close attention to that when you're doing these problems. Find the probability that the cards are both hearts. All right, no replacement. That means you draw a card, it's a heart, you draw another card without putting the first one back, and it's also a heart. Okay, so we're going to multiply these probabilities. I am not about to draw you a probability tree for a standard 52 card deck because that tree, just no. We're not doing 52 little branches and then 50. No. So both hearts. The probability that the first one's going to be a heart. There's 13 hearts out of 52 cards. So there's the probability that the first one's a heart. And we want the second one to be a heart, but we're not putting the first one back. So there's 1 less heart. Now there's only 12 hearts and there's only 51 cards. Let me grab my highlighter here. Just want to highlight the fact that we are not replacing that. That is why that number went down. I had 13 hearts, I pulled out 1, now there's 12. Had 52 cards, took 1 out, didn't put it back, now there's 51. I don't know what 52 times 51 is. I mean, I wish I could lie to you and act like I did know, but I don't. So that's going to be 156, and then 52 times 51 is 2652. Does that reduce? I thought it should reduce. Yeah, it does. 1 out of 17. I'm using a calculator, by the way. Oh, yeah, you can see it in the screen. I don't want you guys over here thinking I was some kind of mathematical genius. Or maybe I do want you thinking that, so... Now, I multiplied because we're talking about pulling out a heart and then another heart. So this is an and probability, this multi-stage experiment, doing something and then something else. Both face cards. Probability of getting a face card. Remember, there's 3 face cards in each suit. Jack, Queen, King. So there's 3 in each suit, 4 suits, 12 face cards. You take one out, don't put it back. Now we've got 11 left. 51. All right, what is 12 times 11? I should know that's 132. And that's out of 2652. Does that reduce? It does. That's 11 out of 221. I don't know if you guys know, I'm kind of using a more basic calculator here. When you're doing these on, a more snazzy calculator, so if we got 132 divided by 2652, it's going to give you that decimal. If you want to change that to a fraction, you have that math button over here, cleverly labeled MATH. The first option, got a little arrow and then frac. That means it's going to convert to a fraction. If you hit enter, it's going to bring up the command. Enter another time will execute the command. So you got to hit enter twice. Once to bring up the command, the second time is going to execute the command. So there's your reduced fraction. So I don't want you thinking that you had to reduce this on your own. All right, so what's the probability that they're both red cards? Well, how many red cards? There's half of the deck. 26 out of 52. Don't use 1/2. That's not going to be ideal to use right here. If you pick out a red card and you do not put it back, now there are 25 red cards out of 51. So here again, I'm just going to kind of accent this stuff. So this stuff is all happening because of this. If I did put the card back, these two numbers would be the same. But because I'm not putting the card back, then these events become dependent events. All right, so 26 times 25 is 650 over 2652. I feel like that's going to reduce. And that's going to be 25 over 102. All right, so pause the video and see if you can find the probabilities associated with those two. All right, the probability of getting a 4. There are 4 4s because there's 1 in each suit. So there's 4 4s out of 52. Maybe that wasn't the best choice of numbers to use because I don't want you to think those are connected. So, you know what? Change my mind because I can do that. I got that kind of power. I'm going to make that a 3. Boom. There are 4 3s. I don't want you accidentally thinking that you got to use the same number there. So there's 4 3s. If I take one of them out, now there's only 3 of them out of 51 cards. So that gives me 12 out of 2652. Let's see if that reduces. It's going to be 1 out of 221. There's my highlighter here. All right, an ace and then a 7. Okay, so the ace, there's 4 of those. And then a 7. All right, so I pull out an ace. I don't put it back. Ooh. How many 7s are there now? Well, I pulled out an ace. That had no effect on the 7s at all, right? There's still 4 7s. There's just 1 less card. Oops, if I scooch that up, you probably want to see that. So I'm accenting with this highlighter the things that are being affected by that replacement. The 7 was not affected by the ace. Okay, those are independent of each other. Whereas 2 red cards, pulling out a red card does affect another red card. But here, an ace and then a 7, the only thing affected is the total number of cards. So we get 16 out of 2652, which reduces to be 4 out of 663. Now, if at any point you guys get something different, if you think I've made a mistake, please tell me, because if I made a mistake, I do want to fix it. It does happen. All right, last page. This is going a little smoother than the last section where we were talking about the cows, the murdering cows. If 4 letters are randomly selected from the word Alabama, find the probability that the letters will spell the word lamb. Now, we're going to do this both with replacing the letters and without replacing the letters. So you just have some letters randomly in a cup, and you just reach in. What is the probability that the first letter you pull out is an L? Well, how many letters are there? 1, 2, 3, 4, 5, 6, 7. Okay, so the total number of letters is 7. There's only one L. So the probability of getting an L, so let me do this. Is 1 out of 7. And then we need an A. Now, I am replacing the letters. So I pull out that L and then I put it back in the cup, mix it around. So we still have 7 letters. There are 1, 2, 3, 4 A's in that cup out of 7 letters. So I have a 4 out of 7 chance of picking an A out. Okay. I put that A back in, mix it around. What's the probability that I pick out an M? I put that letter back, so I replaced it, still have 7 letters, one of which is an M. I put that letter back, still have 7 letters, one of which is a B. So I need to multiply this. Remember that when you multiply fractions, you multiply straight across the top and straight across the bottom. I do not know what 7 to the 4th power is. It is 2401. I don't think that's divisible by 4. It is not. So that's not going to reduce. Now let's do this again, but this time without replacing the letters. Okay. So I'm going to highlight this. We're not going to replace those letters. Okay, so for the L, A, M, B. The L, probability is still 1/7, but now I'm not going to put that L back in there. So now for my second letter, I only have 6 letters to choose from. The L is gone. Of those 6, 4 of those is an A. Okay, so you take out that A. I'm not going to put it back, so now I'm down to only 5 letters. And I'm missing an L and an A. So now what's the probability of an M? There's still one M. And then the probability of a B, now I'm down to 4 letters total because I haven't been putting these back as I've been drawing them. There's one B. Now, this, let's just say that this last letter was an A. I would be down to 4 letters, but I would also be down one of the A's. So I realized I picked a word that didn't have a repeated letter in it. If this last one, let's say I was making the word llama, then that last A, there would be one less A. I would have to take that into consideration. We have 3 out of, 3. Okay, so we're going to multiply that stuff. And I'm going to get 4 on the top, and then 7 times 6 times 5 times 4 is what? 42 times 20, so that's going to be 840, which is divisible by 4. So that's going to be 1 over, is it 210? I'm going to tell you wrong. Yeah, it's 210. All right, so that's going to finish up section 9.2 for us. I mentioned earlier that there's a really cool probability activity that I want you guys to watch. It's 7 minutes, 26 seconds. You can kind of fast forward through it and kind of skim through it. But this is a really cool little probability activity. It uses candy that has to be certain colors to show you how to build an area model for outcomes and use it for probabilities. This kind of stuff is really cool to have on hand when you're teaching, because you can start teaching probabilities. You don't have to go, quite to this extreme, but you can start, with basic probabilities. The idea of, a part out of a total in some earlier grades. So my oldest is in 7th grade, which I really shouldn't say. He's in 9th grade math. I'm trying to think of when he did probabilities. He did probabilities a few years ago, so I feel like it was before 7th grade math level that he was doing some probabilities, just some basic introductions, like, the probability of flipping a coin or rolling a die, that kind of thing. There's also a lot of really cool kids books out there too, dealing with probabilities. There's one called It's Probably Penny, about a French bulldog, I think, named Penny, and the probabilities associated with her. So, but yeah, there's a lot of really cool things out there. But I think this particularly spoke to me because I really liked that area model and how they built it, and how the video wasn't too terribly long. It was, really super cool and engaging and stuff, and something I think that you guys could use in your classrooms someday. So, okay, that does finish up section 9.2 for us.